Hello and welcome to Calculus tutorial. We are still looking at limits, and hopefully by now you have a basic idea of what a limit is. But now we're going to start taking a look at the formal definition of a limit and what that means. It's a little more complicated, and so we're going to take 2 days to sort of do this. So the definition, the formal definition is right here. It's what's in your book, exactly. So let f be a function defined on an open interval, so that's just an open interval of space, containing c, and let L be a real number. All right, so far nothing too crazy there. That means this statement, which is what we're familiar with, the limit as x approaches c of our function is equal to some number L for limit. All right. What does that statement mean? That means that for each epsilon greater than 0, there exists a delta greater than 0, such that if this is true, then this is true. And I'm hoping that makes absolutely no sense. Okay, and so right now I just want to focus on what this sentence in the bullet point says. That means for each epsilon, there exists a delta. Okay, that's kind of what I want you to take away from this right now. For every epsilon, there is a delta. Okay, and epsilon is going to be related to our y values. So if you take a look at the equation here, epsilon is over here with our y values. F of x is just another way of writing y, and our limit is the y value. And delta is going to relate to our x values. So you can see delta is over here related to x, and x is getting closer to c, which is also going to be an x value. So when you see epsilon, that's going to be relating to our y values, and delta is going to be relating to our x values. So they're just the Greek letters. Don't let them throw you off too much. But to really get an idea for what this means, I'm going to have to give you a visual representation. So the one thing I want you to remember, for every epsilon, there must be a delta. So what does that mean? Let's take a look at a graphical definition here. So what it means is if I tell you how close your y values must be to the limit, then you must tell me the x values that will get me that close. So if you're telling me this equation is getting closer and closer to 5 on the y values, then you got to tell me the x values that will get me as close as I want to that number 5. So let me try to keep explaining that. So here I've got a parabola, and we're going to be taking a look at the limit as x approaches 3 of this function. And if you just take a look at it, here is that point. It is exactly 3. But if that limit is true, that means, here are my y values. If I tell you to get really, really close to that y value, you have to tell me how close to the x value we have to get. And this distance here is epsilon, and the x distance is delta. Okay? So, right now, my epsilon is this distance, which is 2.5. Or sorry, not 0.5, approximately. 0.46 to be exact. But if I tell you to make that epsilon smaller, that distance smaller, we're getting closer and closer. Let's say I make it 0.25. Do you see how the delta also changes? It's smaller. For every epsilon, now my epsilon is 0.25, there is a delta. So if I tell you to get within 0.25 of 3. So my epsilon over here is 0.25. So I'm allowed to go up 0.25, and I'm allowed to go down 0.25. You would have to figure out what is the distance down here. How far away from the number 3 am I allowed to get? Okay, so we can do 3 plus just a little bit, and we can do 3 minus just a little bit. And that will still keep us from going above, what will that be, 3.25? And that will keep us from going below 2.75. Now, can we see what that is from the graph? No, it's too small. But there is a number, a boundary, if you will, down here that will keep us in the boundaries up here. And so no matter what epsilon you're given, however far away from 3 you're allowed to go, there is a relationship for delta down at the bottom, okay? And of course, as epsilon gets smaller, so too does delta, okay? So, the definition says that for every epsilon, there has to be a distance down here, delta, to give me that epsilon. And so that's what we're going to start doing algebraically to sort of prove that a limit actually exists. All right, we're going to do mostly simple examples because this is a fairly complicated idea. Okay. Oops, where is my... So, hopefully you kind of have an idea of what that looks like. Now we're actually going to do a guess and check example. And for right now, we are just going to guess and check. So we've got this equation here, nice and complicated. And we want the limit as x approaches -2. It's a nice, interesting one because we cannot plug in -2. So determine the delta necessary for this limit to be true for an epsilon of 0.01. So whatever that limit is, I'm allowed to go up 0.01, and we're allowed to go down 0.01. That's my boundary. And I need to figure out what x values, delta, will keep me within that boundary. So we're going to use the calculator for this. So let's type in the equation here, bring up my fraction bar. We have x cubed minus 5x squared minus 4x plus 20. On the top and on the bottom we have x plus 2. Alright, so now go to our table. So, something close to -2 would be -2.1 is 29. Something on the other side would be -1.9. Alright, so what number are we getting closer? It's kind of hard to see, isn't it? Let's get really close. -2.0001. What number are we getting close to? It looks like we're getting closer and closer to 28. Alright, so it looks like this is going to be 28. But if it's 28, then I should be able to get as close as I tell you. So again, we're going up 0.01, so that means I can go up to 28.01, or I can go down to 29, I'm sorry, what am I saying, 29? 27.99, we added a cent, and we took away a cent. All right, those are my boundaries. So now I'm just going to guess and check until I get something like 28.01 and 27.99 over here, and that will tell me my boundaries for x. So we're just going to sort of guess and check this a little bit. So that was obviously way too close, 28.001. So I'm going to get a little bit farther away. So negative 2.001. Does that get me close enough? It looks pretty good. We see 28.01. But there is that one that pushes me a little bit farther away. So I'm going to go negative 2.000 again. But this one was way too close. What if I do 5? It's a little bit farther away. All right, not too bad. 28.005. That almost rounds this up really obviously, but let's get a little bit farther away. Right now I'm sort of playing with the numbers. What if I go 8? That almost rounds it up. Negative 2.0009. All right, that is almost perfect because that 99 really rounds that up to 1. So let's call that 2.0009. So think about your number line here. Oops. Here's negative 2. And so how far this way? Actually, which way am I going here? Negative 2.009. We were actually going this way, weren't we? How far down are we allowed to go? Negative 2.0009. All right, now how far this way are we allowed to go? So that's going to be like negative 1.99 something. So let's try that. Negative 1.999. Let's try 3 9s. So that's 27.98, and we need 27.99. So we're still too far away. All right. So I'm going to delete some of these. 27 point, let's do 3 9s. That kind of got us, oops, not 27. Negative. Oh well. Negative 1.999. All right, so that got us 27.989. That is really, really close. I just have to get a little bit closer because we're still too far away. The 9.8, yes, that rounds up, but we're going to try to be accurate to 3 decimal places as much as possible. So if we go negative 1.9999, that gets us our 2 decimals. I can go a little bit farther away though, because I get 998. I can go to 990 is really where I want to be. So I can do negative 1.999, and instead of another 9, which is even closer, what if I try a 1? That gets me 990. I'm pretty good till 3 decimal places. So let's call that good. Okay? So we can go all the way down to negative 1.9991. So what is that distance? So when I went this way, we were able to add 0.0009. And when I went this way, it's probably a little bit less obvious what we were subtracting, but that is also 0.0009. 9. If you want to subtract those two, you can. You'll get your number. Oops, I got those switched, didn't I? Sorry about that. Negative numbers, they're all wonky. So we were adding 0.0009 and we are subtracting 0.009. That is our delta. Okay. Our epsilon was adding 0.01, which means we also subtracted 0.01. And our delta is 0.0009. Now I did some pretty fancy guess and checking. If you don't want to get quite that exact, that is certainly okay with me. I'd be pretty okay with this one, I think. That rounds up quite easily. So I'd be okay with that one probably. But given this epsilon, we figured out how far away from 2 were you allowed to go.